Just a few weeks ago, astronomers thought 3i Atlas, the third confirmed interstellar visitor, would quietly drift past Mars without much fuss. But the cosmos had other plans. In less than 48 hours, this mysterious traveler erupted, glowing 6 times brighter than expected, and forming a massive green carbon dioxide-charged cloud, so wide it now stretches to nearly half the size of our Sun. And here's the kicker: Earth's telescopes are already losing sight of it, as Atlas races toward Mars at an astonishing 70 kilometers per second, slipping into the blinding glare of the Sun. That's more than twice the speed of Mercury, the fastest planet in the solar system. At that velocity, Atlas could cross the distance between Earth and the Moon in just over an hour, a trip that took the Apollo astronauts 3 whole days. By late October, as it reaches perihelion, its closest point to the Sun, its speed will climb even higher, pushing nearly 6. For context, the Parker Solar Probe, the fastest spacecraft humans have ever built, needed years of planning and multiple slingshot maneuvers to reach about 200 km. Atlas is doing this speed naturally, purely under the pull of the Sun's gravity. Now here's where it gets even stranger. On the astronomical brightness scale, 3i Atlas has shot up to magnitude 12, around 40 times brighter than it was just days before. That's still too dim for the naked eye, but through mid-sized telescopes, under clear skies, amateur astronomers describe it as a ghostly smudge, barely hanging in the blackness. The faint light comes from its enormous coma, a glowing halo of dust and gas that has now expanded to nearly half the Sun's diameter. Think about that. A physical structure hundreds of thousands of kilometers across, born from a relatively tiny nucleus that scientists estimate is just a few kilometers wide. But the real shocker: 3i Atlas isn't bound to our solar system at all. Its orbit is hyperbolic, meaning this is a one-time only flyby, no return trip, no second chances. Once it swings past the Sun, it will slingshot back into the depths of interstellar space, never to be seen again. This makes its upcoming Mars flyby, just 30 million kilometers away on October 3rd, absolutely historic. It's close in cosmic terms but poses no risk to Mars or its orbiters. For us on Earth, the closest pass has already happened, and at nearly 270 million kilometers away, it was never a danger. No impacts, no meteor storms. What's at stake here isn't survival, it's discovery. That's why astronomers and amateurs alike are scrambling. Within hours of the brightness spike, observatories worldwide lit up with reports. Was this a genuine outburst, a new kind of chemistry, or something we've never seen before from an interstellar traveler? One thing is clear: the window to study 3i Atlas is shrinking fast, and every observation we make now could rewrite the way we understand not just comets, but the galaxy itself. As 3i Atlas dives deeper into the solar system, it's not just racing, it's hiding. The geometry of its orbit is working against us. The angle between the comet and the Sun, called solar elongation, is shrinking fast. By October 21st, that angle drops below 30 degrees. At that point, even the world's most powerful telescopes struggle to separate the comet's faint glow from the Sun's blinding light. In other words, just as 3i Atlas makes its closest approach to Mars, Earth's observers will be cut off. The most dramatic part of its journey, its furious outbursts and fiery interaction with solar radiation, will unfold completely hidden from direct human eyes. By October 29th-30th, when it swings closest to the Sun at just over 1.3 AU, its peak moment of activity, invisible to us, that blackout isn't just inconvenient, it's final. 3i Atlas is on a hyperbolic path, a one-time visitor from another star system. Once it vanishes into the Sun's glare, any mysteries it leaves unsolved will stay unsolved for generations. So astronomers are racing the clock. The only way to keep watching Atlas is to hand the job to spacecraft already orbiting Mars. These orbiters, built for planetary science, are suddenly being retasked as cosmic sentinels, ready to capture one of the most fleeting encounters in modern astronomy. On Earth, the scramble for data has been intense. The Hubble Space Telescope forced an emergency schedule change to capture ultraviolet and optical frames before Atlas faded. Each exposure had to balance detail against the risk of overexposing the ballooning cone. Then came the James Webb Space Telescope, winning a rare emergency slot for mid-infrared observations. What it found shocked astronomers: an unusually high carbon dioxide to water ratio, 7.6 to 1, far above what's ever been measured in ordinary comet. That discovery alone sparked a wave of requests across observatories worldwide. Gemini South in Chile pivoted to track subtle shifts in the comet's structure and color, while NASA's SPHEREX surveyor adjusted its scans to track the comet's volatile gases as it moved through different solar zones. Each telescope brought a unique piece of the puzzle, but each also faced limits: bad weather, short observing windows, or the unstoppable narrowing of solar elongation. Behind the scenes, this turned into a global coordination effort, more like a planetary defense drill than normal comet work. Directors shuffled schedules, teams argued over filters and exposure times in late-night Slack threads, and data pipelines ran non-stop to process and share the precious frames. Everyone knew the blackout was coming. Once Atlas slipped behind the sun, Earth would be blind. That's when the torch passes to Mars. Orbiters like MAVEN and TGO, never designed for comet chasing, now have a once-in-a-lifetime chance to track a rogue interstellar traveler up close. In that moment, Mars becomes the solar system's best observatory, our only set of eyes on a cosmic visitor racing through history. Scientists and engineers around the world are in a race against time. Missions orbiting Mars, NASA's Mars Reconnaissance Orbiter, ESA's Mars Express, and even the European Trace Gas Orbiter are being reprogrammed on the fly, all to capture a once-in-a-lifetime view of this interstellar traveler. NASA's HiRISE camera, famous for zooming in on oats as small as a desk from orbit, is pushed to its absolute limits. Imagine trying to track a comet flying at 58 kilometers per second. Millions of kilometers away. That's like trying to photograph a single firefly while riding a speeding bullet. To make it work, teams at JPL and the University of Arizona are adjusting exposure times, running simulations and squeezing every second of observation time they can. One wrong move and the comet could slip past unnoticed, or worse, the camera could be damaged by sunlight glare. Meanwhile, ESA's Mars Express brings its powerful stereo camera into the mix, designed to capture sweeping images of the comet's massive coma and tail. Its color filters will help separate dust from gas, while 3D stereo pairs could reveal hidden structures inside the glowing cloud. And then there's the Trace Gas Orbiter. Its spectrometers are fine-tuned to sniff out rare gases like carbon dioxide, water vapor, and maybe even organic chemicals never before seen in a comet from beyond our solar system. But perhaps the most exciting angle comes from NASA's MAVEN spacecraft. With ultraviolet eyes, it can detect glowing emissions from oxygen and carbon, helping explain the comet's mysterious green glow. Is it just the usual diatomic carbon, or is something far stranger happening in this alien visitor's atmosphere? Every mission has to fight for observation slot. Emergency meetings are held, software patches are uploaded at the last minute. Engineers juggle safety protocols, dust hazard models, and instrument limits. It's not just about the technology, it's about human ingenuity and international teamwork. And then the payoff. The comet's coma suddenly shifts from dull red to an astonishing neon green, expanding to more than 600,000 kilometers wide, half the size of the sun itself. Astronomers are stunned. This is no trick of light or exposure. The transformation is real. Something extraordinary is happening at the heart of 3I Atlas, and the data pouring in may completely rewrite what we thought we knew about comets from beyond the solar system. What shocked astronomers next was the absence of something they expected to see. Normally, comets glow green because of C2 molecules, that familiar carbon signature we've seen time and time again. But in this case, nothing. No swan bands, no trace of the usual carbon fingerprints. Instead, the spectra told a different story. In August, the James Webb Space Telescope revealed something extraordinary. The comet's atmosphere contained a CO2 to H2O ratio of nearly 8:1. That's completely upside down compared to most comets, where water usually dominates. This tipped scientists off to another culprit: atomic oxygen. When sunlight and high-energy particles smash into CO2 and water molecules, they split them apart, releasing oxygen atoms. These atoms emit a bright green photon as they drop back to a stable state. And in 3I Atlas's CO2-rich coma, this reaction is happening on a massive scale, essentially turning the comet into a factory for green light. Other explanations were tested: fluorescence from carbon monoxide, dust scattering, even exotic plasma effects. But the data just didn't. The dust spectrum hadn't changed, and carbon monoxide was missing. The evidence kept pointing back to atomic oxygen. For Dr. Lena Sato, leading the spectroscopic team, it felt like chasing a moving target with a constantly shifting personality. Every spectrum showed a system in flux, a living chemistry lab millions of kilometers from Earth. And far from being a disappointment, the missing C2 was a revelation. It suggested that 3I Atlas might be following rules completely alien to our solar system's comets. Its eerie green glow has now become its signature, a fingerprint of interstellar chemistry shaped in another star's nursery. But the surprises didn't stop there. As scientists studied its structure, they noticed something truly bizarre: an anti-tail. Instead of streaming away from the sun like a normal comet tail, this streak pointed directly toward it. Visible in both Hubble images and ground-based telescopes, the anti-tail refused to fade. Why? Because 3I Atlas isn't fueled by water ice. It's dominated by carbon dioxide. Its gas jets erupt unevenly, blasting large, heavy dust grains sunward. These grains, some at least 10 microns across, are tough enough to resist solar radiation and survive far longer than expected. The result is a real physical anti-tail stretching tens of thousands of kilometers into space. Plasma physicists suspect electromagnetic forces may also be at play, with charged dust grains dancing against the flow of the solar wind. Whatever the case, 3I Atlas has broken the Comet rulebook once again. For all the excitement around 3I Atlas, some theories have gone off the rails. Talk of alien tech, engineered plasma, or even interstellar machines, but so far the evidence doesn't support anything exotic. The anti-tail, as strange as it looks, can still be explained by natural comet physics pushed to their extreme limits. As Dr. Rafael Ortiz from the Mars Orbiter team put it, if you want proof of the extraordinary, you first have to rule out the ordinary. And right now, the anti-tail is standing as a triumph of natural mechanics. But the real test is still ahead. 3I Atlas is approaching perihelion, its closest swing by the sun, and this is when things could get unpredictable. Models split into three very different outcomes. Terrific. Some predict a slow fade, as the comet's ices burn off and its coma shrinks away. Others warn of a final flare, a sudden burst of brightness caused by hidden carbon dioxide pockets, or even a partial collapse of the comet's surface. And then there's the most dramatic scenario: total disintegration. If the nucleus is as fragile as scientists suspect, perihelion could rip it apart, scattering fragments into space and erasing the comet in a flash of light. Mara Valente, a comet dynamicist, calls the coming weeks a stress test for every comet theory we have. Her team is running simulations that map out dozens of possible fates, each with its own fingerprints. A smooth fade, that means simple outgassing. Wild jumps in brightness, that could mean fragmentation. And if the eerie green coma persists after perihelion, it would reveal deep reservoirs of carbon dioxide unlike anything in our solar system. This is bigger than just one comet. 3I Atlas is a probe from another star system, carrying chemistry shaped in a distant nursery. Its survival or destruction teaches us how interstellar objects behave, how long ices can endure, and whether our models are strong enough to predict the life cycles of these cosmic wanderers. The timeline is locked in. Mars Orbiter data drops in early October. Perihelion hits on October 29th and 30th. Then Earth-based telescopes regain their view in November. Each milestone could either confirm what we think we know, or force astronomers to rewrite the rulebook. For now, 3I Atlas is more than just a comet. It's a live experiment at interstellar speed. And the ending to this story, nobody knows yet.